Now we're ready for an exercise. The exercise will be to find the phase fraction associated with the volume fraction by point counting. As mentioned, we're going to use a 10 by 10 grid. Here's the image. Here's the 10 by 10 grid. Now we need to go row by row and evaluate the points on this grid. A half, 1.5, 2.5, 3.5, 4.5, 5, 5.5, 6, 6.5. So now I've identified that 6.5 out of 100 points are in the second phase, the dark phase, Pearlite, which easily works out to an estimation of 6.5% Pearlite. So now that we've estimated the amount of second phase, now we can estimate the carbon content for this steel. So now we can use what we've learned about the phase diagram to calculate the carbon content in this steel. Now, how are we going to do that? Well, starting with making some simple assumptions that starting from austenite, the material cools slow enough to 727 degrees Celsius that we have an equilibrium amount of austenite and ferrite, and also that there's not a significant enough amount of other alloying elements to throw this phase diagram, the iron carbide phase diagram, off too far, to not translate the lines on the phase diagram. So making those assumptions, if we cool from austenite, we know that just above 727 degrees C, the transition temperature, we can determine how much austenite and how much ferrite we will have based on the lever rule. The lever rule says that the quantity or the fraction to the left represents the amount of austenite divided by the whole. Basically, the weight fraction of austenite is the nominal composition minus the carbon composition of the ferrite divided by the difference between the carbon composition of the austenite and the ferrite. And we know the carbon composition of the ferrite and of the austenite and the ferrite again. So we can solve that equation to determine what the amount of austenite is going to be. Now, again, coming back to this assumption of slow cooling, slow enough cooling, which is a safe assumption for our normalized steels, especially vintage steels, then that austenite will transform to pearlite and then cool down to the product that we're going to use. Now, if we solve the lever rule with these two unknowns for carbon content, so here's the C naught, then we essentially have the reverse equation. Now we're determining the carbon content from the pearlite content, and we can easily plot that, and I've plotted that here, from 0.02 up to 0.76. The increase of the amount of pearlite with the increased amount of carbon is linear. So going back to the micrograph that we evaluated, if we said that micrograph has 0.065 or 6.5% pearlite in the microstructure, then that has got to be somewhere, based on our assumptions, around that amount of carbon. So about 0.07% weight percent carbon. To summarize the results of what we just calculated from the plot, we had identified that there was about 6.5% volume fraction of perlite. And on the plot, that corresponded with about 0.07% carbon. You can also plug that 0.065 perlite fraction directly into the lever rule equation, where carbon weight percent equals 0.74 times the perlite in weight percent plus 0.02. Here's our perlite fraction, and plug and chug, and we get 0.07. ASTM E562 also has a table, table 3 here, that helps you predict the number of fields that you're going to have to observe or make measurements of in order to achieve a certain amount of relative accuracy. For our program, probably 20 to 30% of relative accuracy will be sufficient. We will oftentimes be looking at 10 to 20%, sometimes higher, sometimes lower, percent of second phase. And we're going to be evaluating 100 points for each image. So even though we're only going to start by evaluating one image for each feature, in the eventuum, we're going to be evaluating more than one. We'll probably get to the point where we evaluate 4 or 5 images for each feature to achieve the amount of accuracy that we need for this program.